Image classification involves identifying the main object or subject within an image or assigning each image to a specific category or class. It operates on the principle of supervised learning, where a model is trained on labeled images. Once trained, the model classifies new, unlabeled images by recognizing patterns learned during training. Common use cases include recognizing objects in closed scenarios, such as identifying fruits or animals. Typical models utilized include convolutional neural networks, CNNs, like ResNet, AlexNet, and MobileNet, widely integrated within Azure's computer vision services to streamline implementation and development. Object detection differs significantly from classification, as it identifies and locates multiple objects within an image, providing bounding boxes around each detected object. This technique combines classification and localization, identifying the category of each object as well as its position. It employs methodologies such as selecting candidate regions or anchor boxes where objects might appear. Applications of object detection cover a wide spectrum, from real-time video analysis in autonomous driving systems to security and surveillance solutions. Common deep learning models include YOLO, You Only Look Once, Faster RCNN, and SSD, Single-Shot Multi-Box Detector. The primary distinction between image classification and object detection lies in their objectives and outputs. Image classification aims at assigning the entire image to a single category, making it effective for singular dominant object recognition problems. Conversely, object detection outputs involve pinpointing specific locations of one or multiple objects, providing detailed positional and categorical information through bounding boxes. This distinction is crucial when selecting the appropriate approach for your application scenario, significantly influencing the technology employed, resources required, response time, complexity of implementation, and precision needed in the final application. Adopting an image classification model is suitable when the primary focus is understanding the overall context or dominant object within the image. Examples of use cases include tagging images with specific predefined labels, such as animal species in photos, product categorization, or identifying image content for moderation purposes. Classification frameworks like Azure Custom Vision Service simplify the process by providing a user-friendly platform for training custom classifiers without extensive technical expertise, making them ideal for streamlined, single object-oriented applications or solutions that do not demand detailed object positioning within images. Selecting object detection models is imperative when merely classifying isn't sufficient, particularly in scenarios requiring explicit detection and localization of multiple objects or instances within images. Example use cases comprise real-time monitoring environments, autonomous vehicles recognizing pedestrians, traffic lights, signs, and more. The Azure AI Vision Service, through facilities like Object Detection APIs and Custom Vision's object detection features, streamlines development, considerably reducing the barrier to implement complex applications. It ensures high precision and detailed results via bounding boxes and labeling, critical for providing actionable insights and detailed analysis. From a technical standpoint, image classification models generally embody less complexity as they analyze single identities per image. This characteristic reduces computational hours, model training complexity, and relative resource consumption. Conversely, object detection models involve significant computational effort in both training and runtime phases since they handle concurrency in object recognition and localization. Techniques like anchor matching and intersection over union, IOU, calculations add complexity. Consequently, choosing between these methods requires evaluating project constraints such as resource availability, latency requirements, computational infrastructure, and software scalability considerations listed clearly in project goals. Computational power differs greatly between classification and detection methodologies. Image classification typically demands fewer computation resources, running efficiently even on low-powered edge devices or limited processing infrastructures, suitable for applications that prioritize rapid inference over detailed spatial analysis. Object detection, however, must manage higher computational overhead due to bounding box predictions, positional accuracy, and multiple concurrent object classifications. These models often require more robust hardware, cloud-based GPUs, or powerful processing architectures. Using Azure infrastructure can alleviate burdens by providing flexible cloud AI services, scaling disparate computing power needs across diverse scenarios. Accuracy expectations dictate model selection significantly. Image classification models achieve high accuracy under well-defined conditions where object positions and counts within images are predictable and uniform. Precision in classification context refers mainly to correct categorization rather than spatial accuracy. Object detection models, however, deliver enhanced precision through bounding boxes around identified objects, benefiting applications that demand spatial awareness and precise object placement. This increased positional accuracy is crucial within critical applications like self-driving technologies, robotics, advanced security systems, or environments where analyzing multiple concurrently occurring objects is essential. Latency impacts the user's perception of model effectiveness, particularly relevant in real-time contexts. Image classification tasks usually involve minimal processing times, partly because they handle single categories per image. Thus, scenarios requiring very low latency, such as real-time video streams or rapid batch processing, often prefer image classification if spatial awareness is not required. Object detection inherently introduces higher latency due to complex methods involved in object localization, bounding box generation, and concurrent object classification. Therefore, applications that demand extremely low response time and simple analyses are typically more suitable for image classification solutions. Microsoft Azure offers comprehensive capabilities to implement both image classification and object detection projects. For image classification, Azure Custom Vision Service provides intuitive training and deployment facilities, making model creation straightforward for users of varying expertise levels. Azure AI Vision APIs support object detection capabilities integrated within diverse environments, including cloud and edge deployments. These solutions utilize Azure's scalable infrastructure, ensuring provision of sufficient resources, ease in scaling solutions according to demand, and seamless interoperability between various Azure AI services. Flexibility in integrating additional services, such as Azure Functions and Logic Apps, enhances solution customization potential. Costing strategies influence strongly when choosing between image classification and object detection within Azure services. Classification models typically unify lower-cost structures due to less computational intensity and streamlined resource utilization. Conversely, object detection, with greater resource-intensive requirements, may carry higher operational expenditure. Thoroughly evaluating budget constraints, cost management, and value gained against expenditure becomes vital. Azure AI's flexible and transparent pricing structures offer clear insights into allocating and managing costs effectively. Tools like Azure Cost Management assist in budgeting, monitoring expenses, and optimizing spending, fostering cost-effective deployment strategies aligned with technology selection. To facilitate informed selection between image classification and object detection models, a decision-making framework includes application purpose and the role of spatial information, computational resources and response time tolerance, precision and accuracy requirements, cost implications, and Azure budget considerations. Assessing these critical factors thoroughly leads to optimal selection decisions. Azure AI resources, powered by Microsoft's flexible and powerful computing infrastructure, adapt widely across differing scenarios, ensuring that chosen methodologies efficiently align with and fulfill distinct project goals and user expectations effectively and seamlessly.